we do first here?
We would add NaO to an HCl.
And that gives us the diazonium.
And then add, wait, why didn't you add the, couldn't you add the BR? Oh, wait.
Yeah, I think we should,
Yeah, you didn't.
as long as we're doing that, we might as well do the chlorines first.
Yeah.
Or,
Because you started
yeah.
off with the benzene in the beginning, not with anything.
we should add the bromines first, because what's the advantage of this nitrogen
It's
here?
gonna put them on all places.
This is a strong activator. We want to hold on to this because this is such a strong activator. That overcomes the problem we were talking about before.
And then you can do the benzenes.
We talked earlier about how sometimes we have to moderate the activating power of an amine, but here we want it to be strongly activating because we want to get as many things added as possible. And will the bromines go where we want? Well, yes, because this is an O and P director. We want them to go to every single possible O and P position. And now, as I think you're seeing, now we can do the diazonium thing. And then
CuCl.
and that'll give us the product that we want. There's one other thing that is useful that we can do with the diazonium. Which is that we can just replace the diazonium with a hydrogen. So we need to have memorized what this reagent is. I don't know if you remember that from class.
No.
So this is H3PO2. Is that something your instructor mentioned? Okay. By the way, this is not phosphoric acid, which is much more common. That would be PO4. This is like hypophosphorus acid or something like that. So this is an unusual acid to be using, but this is the standard acid to use in this case. Hypophosphorus acid, yeah, H3PO2. So there's just a whole bunch of memorization in a lot of the reagents that we've seen. And this replaces the diazonium group with just a hydrogen. Now, this is interesting because before this, we'd only learned one way to replace a functional group with a hydrogen. What was the other way we learned to replace a functional group on? Yeah, the reversible sulfonation. But now we have another way to get rid of the functional group. That only works for sulfone groups, so that's not very flexible. But now, if we can just get to the NH2, then we can get rid of it altogether. That means that we can now put nitrogens on just for their directing abilities. Even if we don't plan to keep them forever, we can put the nitrogen on and then take it off eventually. So let's try this synthesis.
HNO3 and H2SO4. And PO2 and FeBr3.
No, first you have to turn it into NH2.
No, because you wanted meta.
Oh. Isn't there two ways you could do this?
Yeah,
Because you could first turn it into an NH2, block the para, add the BRs, then get rid of the azide or diazonium, whatever. Or you can,
Yeah, just do the NO2 on the BR and then make it into.
it seems like it would work fine. So now you're going to do the diazonium reaction here. Okay, that's not the way they did it in the book, but that actually seems fine to me.
what's the way they did in the book?
In the book, they added 2 equivalents of HNO3.
And then turn them both into BRs.
Right, but your way seems fine too. So in the book, they did this. Maybe this is this a little shorter? This is a little shorter because here you have to put in the bromine and then turn this into a bromine. Whereas here, you just turn these into a bromine together. So I think your synthesis is good. This is a little bit more elegant because there might be 1 or 2 fewer steps. Because here you had to add bromines in 2 different ways.
But don't you always say that it's harder to add something to NO2 when it's already there? It doesn't matter if it's
That's
the same
true.
thing.
That's true. Nevertheless, it's still possible. The only thing that can't work is a Friedel-Crafts once
And
there's an
would
NO2.
it be just as hard to add an NO2 there as it would be to add a BR?
Yeah, actually, that's a much better answer. Once we've added 1 NO2 group, it's not any harder to add a second NO2 than it is to add the bromine.
It doesn't matter.
Yeah, remember, what matters is who's already on the ring, not who's coming into the ring. It would be very hard now to add a 3rd substituent, but we're not trying to do a 3rd EAS, electrophilic aromatic substitution, but that's not what we're trying to do. Well, let's do it the book's way. What would we do next with this?
Then we would add CuBr and heat.
To this?
Oh, no,
First
you
you
have
have
to
to-
turn them both into NH2s.
H2PD.
Yeah, first we have to reduce them.
And then turn them into diazoniums.
Then we can turn them into diazoniums.
And then have H2PO2.
Oops.
2 equivalents.
No, you don't need to. You just turn them both into
Oh, okay.
BRs.
Yeah, we're not actually trying to replace these with hydrogens. We're trying to replace them.
I wrote it wrong then.
We're trying to replace them with bromines.
Yeah.
Okay, now I think the approach that you were suggesting, that seems like it would work fine too. We could add a bromine here, and then you were suggesting that we should turn this into the diazonium. I don't see any reason why that wouldn't work.
Isn't there also, like, could you do it a different, much longer way?
Probably, like,
First, okay, you first, turn the NO2, you put 1 NO2 on there, and you turn it into an NH2, and then you add an SO3H to para, to block the para, and then you add BRs that would both add ortho, and then you get rid of the NH2 and the SO3H.
all right, so you were saying first,
Okay, so first you would add an NO2,
okay,
then you would turn it into an NH2, then you would add an SO3H,
That would work.
Then you would add 2 BRs.
That would work.
Then you would get rid of both the SO3 and the NH2.
I don't see why that wouldn't work. All right, yeah, but that would definitely be inferior because there's way
Yeah.
more steps. But yeah, that would seem like it would
So
work too. Yep, good.